So actually yesterday we introduced finally the group G spin. So I can change my title now and move back to lecture 1 since the title has changed, right? So an entirely new topic. So let me remember where we are. So yesterday I explained you how if you take V Q vector space plus a quadratic form of signature over the reals n2, so n positive eigenvalues and 2 negative ones. To that we associated first of all the group G, which is G spin of V, and we associated also Hermitian symmetric domain. And if you take K a compact open subgroup of the adelic points, we had defined then the Shimura variety that we'll be interested in as a double quotient. And in particular, and actually this we wrote as to give a complex structure as a finite union of the Shimura varieties that we saw in the lectures of Jose, okay, over finitely many representatives, gamma G. And in particular, if you take L inside V quadratic lattice, idest Q restricted to L is integral valued on L, okay? Then to this actually we associated a compact open subgroup, which was the intersection of the adelic points. We remember that G is a subgroup of the units of the even Clifford algebra of V. So we can intersect the adelic points with some subunit group of the adelic points of C plus V star. So, and then we get, we wrote ML to be simply MKL, okay? And, and I told you that, so we will choose also for reasons that we will be apparent later when I will talk about integral models, but let me write it right away, otherwise I'm sure I will forget. We also choose L a maximal quadratic lattice in the sense that there is no intermediate lattice between L and V on which Q is integrally defined and strictly contains L, so it's maximality with respect to inclusion. Okay, and actually, so this is an assumption that I will make from now on, so I will not forget. Then we have our ML. So this is actually, I forgot the C here because I mentioned yesterday that this can be defined as a variety of the reference field, and this is a variety defined over Q if n is bigger or equal to 1. In fact, for our proof, as I will explain, we will need just n bigger or equal to 2. So we're definitely in this situation. Okay, and yesterday I mentioned, and I want to stress it again, even if I won't write anything, that for this Shimura variety, there are not known modular interpretations for n large enough. Okay, so for n equals 0, we already saw in the example that the variety that we are getting here classifies essentially CM elliptic curves, where the CM by CM, the CM is given by the imaginary quadratic field defined by C plus of V when n equals to 0. For n equal 1, you can get, in this way, modular curves. For n equal 2, we saw yesterday that we can get Hilbert modular surfaces. For n equal 3, you can get the Siegel threefold. There are connections to moduli, or at least moduli of periods of K3 surfaces, for example, for n equal to 19. But then from some level on, there are not known modular interpretations of these varieties that will create problem when one wants to define models over Z. But here maybe I can add that this is a variety defined over Q, each of dimension n. Okay? Okay, so the goal of today is to show you that even if these varieties don't have modular interpretations, so we are a bit disappointed, they have a very rich structure on the other hand, and so that you get excited again after the disappointment. And I want to explain you how parallel to what Jose did, how given representations of the group G, you can cook up interesting local systems and sheaves on those varieties. Okay, this is not really completely related to the theory of automorphic vector bundles that Jose explained, but still, for us, it will give interesting sheaves. Okay. So the remark is the following, that so we have a functor that goes from algebraic representations of G. So you have representations really on Q vector spaces to local systems over MKC. It can be the general here. And actually, it's very easy because you simply take your Q vector space and then you perform the same construction that we did here by adding here on the left-hand side also the W. And now the GQ will act diagonally on these factors and also on W. And actually, this goes so over MKC, and these I will define to be V, the realization of this representation. And I want to stress that I will get in this way a local system of Q vector spaces. Okay? So if you have interesting representations of G, then we automatically get interesting local systems. So let's see two examples. Or actually, maybe I can say even more. Yeah. So I can also go from local systems over MKC. I can also get to the word of vector bundles with integrable connection. Because if you have, say, one of our local systems, I can associate what I call V the RAM. okay, which is simply what you can think of. So I simply tensor over Q with the structure sheaf, and my connection is simply 1 tensor D, so that the solutions of my integrable connection on this vector bundle is simply given by the complexified local system associated to this Q local system. Okay? And there are actually, in this construction, there are extra properties. Because these local systems and this diagonalization are actually variation of our structures. And for that, remember, if you have an element Z in our symmetric space, this, we said, we can be interpreted as a negative definite plane inside the real vector space. And to that, we got a map from G spin of H, which is our Deligne torus to G of R. Okay. So in particular, if I take an element, hence, given an element, so MK, we said, is a double quotient of that thing. So if I take a representative which is given by a pair Z comma G in my double quotient, I get, by composing the map, so of 20Z here, I have such a map from this torus to GR. Okay, I can compose my map HZ from S to GR to GL W of R. Okay, and in particular, over C, I get a map from C star times C star on the automorphism group of the complexified vector space. That depends, of course, on the base point. And we know very well what are representations of C star times C star algebraic representations on vector space. It's simply equivalent to give a bigraduation on WC, right? Demanding, for example, the first variable acts as Z to the minus P here, and the second variable acts as W, say W's minus Q, for example, or any convention you want. Okay, so for any base point on your, for example, vector bundle, or the complexified local system, you get a big graduation of this type. So that looks very much like pointwise having a Hodge structure on your vector space. Okay, and furthermore, so in particular, our V de Rham inherits a filtration given by, well, fil J of V de Rham. I give you the fiber over a pair ZG. This is simply the sum over all indices P bigger or equal to J of the bigraded objects that I've defined associated to my Z. Okay? So in my picture, I can enrich the structure by having this graduation, and at on W de Rham having such filtration, such increasing filtration. And the point is that this field J of W the RAM inside W the RAM are sub-vector bundles. So they vary holomorphically, even if I've defined things just on the fibers. Okay? Okay, so a little bit maybe too fast. And yes? Sorry?
What is the essentially, I mean, every
No, not every local system. Yes, you get some local system. Yeah. I mean, it wants to say that, say this has just one component, which will be our case. It means that when you pull it back to D, which is simply connected, then you can trivialize. It inherits also an extra action of G, if you want. But, yeah, I don't know if you can really characterize the image besides saying this. Okay, so let's try to see two examples where we view all these more slowly and in practice. Okay? So example one. Well, we said that our group G spin is a central extension of SOV. Hence, it really gives a nice representation on the vector space V we started with, right? And then for every pair ZG, what do we get as the associated B graduation? VC. So remember that this Z corresponds to, I'm using now the second interpretation of my Hermitian symmetric domain that gave us the complex structure. Okay, so these are the lines in VC with the property that Q of Z is equal to 0 and Z bar, never remember if, did I get positive definite or negative definite? Maybe the negative definite. Modulo the action of C star. Okay, so given our Z, I have in particular inside V of C a line, which is specified by our choice. I also have the image and a composite configuration of this line, okay? And then I have the orthogonal complement of these two lines, of this plane. Okay? So this actually is the complexified of the negative definite plane that you have in the real manifold interpretation of the symmetric domain. Okay, then it turns out that this is simply VC. Let me get the numbers right. I think it's 1 minus 1. This is my VC minus 1, 1. And this is my VC 0, 0. So the fact that the sum of the things that you get are 0 comes from the fact that this quotient, it's a quotient map where the GM, the center, maps trivially in SO. Okay, very nice. So our interpretation as a symmetric domain gives naturally this big graduation that here has been defined in a slightly more abstract way. Okay? And in particular, so to V, we associate a V Betty Q, a V drum, and I will be especially interested in field 1 of V drum that only captures, in fact, this first piece here, right? These I will denote by omega, and for us it will be the crucial objects to study Faltings heights of CM points. It's called a tautological bundle. In particular, that my omega on a pair z comma g is what I wrote there, C of g, z in C z inside VC. And in particular, my tautological line bundle inherits a natural metric. A metric on omega by demanding that if I take my z in omega, so I give you now the norm of the section z inside omega, then I demand that the norm is simply given by, well, this is negative. I simply change the sign, what I get there. So this is called Peterson metric. Okay? So we will have integral models. This omega will be extended to a line bundle over the integral model, over variety over z. I will get a metric at infinity. And in this way, I will get a metrized line bundle. And it's the degree of the pullback of this metrized line bundle to same points that I want to compute. Okay. So this is one thing. I have another example. Because we said that the group G spin can be realized inside the automorphism group of the Clifford algebra. Okay. Here I simply take an element G. I view it inside C plus V star and let it act on C of V by left multiplication. Okay? Okay, so I have another nice representation W, of which I can apply my machinery and see what kind of local system I get. Okay? And now if one computes what happens, so then in our case, in this case, for every pair Z comma G in my Shimura variety, my CV tensor C gets a big graduation, which is actually of the type of abelian varieties. So it's a variation of odd structure than CV of type -1, 0, 0, -1. Okay? And in particular, this will lead us to the definition of an abelian variety over our Shimura variety, which is called the Kuga-Satake abelian variety. And now you also see why we needed some effort to pass from the orthogonal group that is better known to us to G-spin, because the representation that factors through SO all have this property that the sum of the P and Qs are zeros, and if you want to get an abelian variety, you have to exceed that and get things of weight -1. Okay? So let me elaborate on this. So in particular, taking a lattice L and K is equal to KL, well, we have seen that, I mentioned yesterday, but I will see it again, that in this case, with our choices, also L maximal, the quotient can be written not simply as a joint union of finitely many connected components, but simply as one connected component, at least for n bigger or equal to 2. Okay, and our gamma preserves L and C of L. Okay, because remember how our KL was defined. Okay, so it's really fixing some integral structure on the Clifford algebra. So this implies in particular that our arithmetic group inside GQ, when you map it to SOV, will in fact respect the lattice L. And when you map it to the automorphism group of C of V, will respect C of L. So we can refine my V Betty to a Z local system whose fibers are locally isomorphic to L. And we can also refine the Q local system defined by the Clifford algebra using what I wrote on the last blackboard. To a Z local system COV Betty, okay? And in particular, using the fact that I have a decomposition of the complexified vector space CV fiber-wise of this type. So it's -1, 0, and 0, and 0, -1, thanks. Thanks. To a Z local system, CV Betty, and in particular, we get over MLC an abelian variety defined by taking our local system tensored with R, and then having such structure simply implies that on this real vector space you are defining a complex structure, and then you mod out by a lattice And this will give us a complex torus that claim it's an abelian variety. Which is called the Kuga-Satake abelian scheme. So there is an issue about polarization that we need to algebraize this complex torus, but I'll leave it aside. And also there are issues that these not really smooth manifolds, the group gamma acting might have fixed points, so this abelian scheme doesn't really exist exactly as in the moduli space of abelian varieties. But let me also ignore this issue. Okay? Okay. Finally, there is an interplay between these two representations. So far, our Shimura variety, MKC or MLC, has an abelian scheme and some bizarre-looking Z local system. And we can relate the two and make sense of what we heard yesterday in the case of Hilbert modular surfaces, that on this modular variety, this abelian scheme has or doesn't have special endomorphisms. Does it mean that we have special endomorphism?
Well, what is the Riemann form on your CV value?
I have to fix a polarization. So the point is that you can always find a Riemann form on CV, which is not unique, but it exists, such that the map from the G-spin to the automorphism group of CV factors through the symplectic similitudes, GSP, of CV with that form. If I want, I can look it up in my notes, how one can find actually examples of such forms.
It's not unique.
It's not unique.
You just choose one. Okay.
You choose one. There exists one. It's not unique. Okay. Moreover, so if I consider the map from V to the endomorphism as a Q vector space of CV, that is given by taking an element little v and taking left multiplication it turns out that this is a homomorphism of G representations, where here I can write this as CV tensor CV dual. This is a representation. The dual is a representation. The tensor is a representation of the group spin. Okay, I'm not going to prove this, but one can prove it. And since I said that the construction that goes from representations to local systems, shifts with connection and so on is a functor, whenever you have a map of representations, that translates into a map of all the realizations that we have given. So this gives maps of Z local systems from my, and this will be the crucial thing, from my V Betty, say over, let me work from now on with the Shimura variety defined by L, so that I also have integral structures, okay? From V Betty, so local system of Z modules, to, well, the Betty realization of CV, that now that I've made some effort to introduce an abelian variety, I can simply write as the endomorphisms as local systems of the Betti homology, the relative Betti homology of my abelian scheme relative to the base MLC. Okay. So in particular, yeah, okay. So this will be the fundamental thing that we want to consider. And of course, you have also the RAM analogs. So from the RAM, the RAM of this, you get to the endomorphism of H1, the RAM homology of your abelian scheme relative to ML of C. And that's compatible with the filtrations, and it's compatible with the connections. Okay, so why is this useful? Because now we can make sense of what we heard yesterday of seeing when, if you have a point of our moduli, or our Shimura variety, you have above it this abelian variety, and you can make sense of what it means for an endomorphism of this abelian variety to be special. When is it special? Well, if you have an endomorphism of your abelian variety over that point, that induces, of course, an element in the endomorphism, and you say, well, it will be special if over that point, this specific endomorphism lies in the image of L Betti. Okay? So we say, well, we can then define for a point ZG inside MLC when an element F, which is an endomorphism of our abelian variety over the fiber ZG is special. Well, it will be if and only if the induced element in the endomorphism of H1 A ZG, well, we tensor with Q because here we are considering the endomorphism algebra. Lies, well, I could say lies in the image of V Betti. I prefer to do something more because associated, so we consider here the lattice L, but you can also consider the lattice L dual, which is slightly larger, right? On which, again, your arithmetic group acts and to which you can associate a Betti realization lies in the image of V Betti dual, which is the realization of L dual. So we said to this lattice, we define an integral structure on V Betti Q. You have another integral structure given by the dual lattice. This embedding is given by the bilinear form that we have on V. So it's slightly larger. Okay. And in fact, the bilinear form on L defines a bilinear form on V Betti, so that the dual that here I've defined simply as a realization is really the dual with respect to the induced bilinear form on V Betti. Okay, so this dual here as, I mean, the two meanings that you can give to it using these two facts are the same. And one can prove, okay, Vibetti, so that Vibetti dual is the dual of Vibetti. And in fact, one can prove that the quotient of Vibetti modulo dual modulo Vibetti is canonically isomorphic to the constant sheaf L dual modulo L. And this simply comes from the fact that our arithmetic group gamma, it acts on L, it acts on the dual, L dual, but it acts trivially on what is called the discriminant group, which is L dual modulo L. As gamma acts trivially on L dual modulo L. Okay? Also, if we have an endomorphism, if F is an element in the and 0 A Z G, which is special, it turns out that if I take the crystalline, the Betti realization of F inside the endomorphism of H1 A ZG Z tensor Q, then so this will be, since it's special, L of something, L of some element V for some inside V Betti dual evaluated at ZG. And then I can consider the quadratic form on the element V that gives rise to this Betti realization. Okay, this will be, since this is a bilinear form on my Z local system, well, it will not be in, so the bilinear form is integrally defined on V Betti. If you go on V Betti dual, it will be an element of Q. And in fact, it turns out that this, if you take multiplication by M on as a rational isogeny on my abelian variety, this is really equal to F composed F. So there is also a relation between the quadratic form on my special endomorphisms and the multiplication, the self-multiplication of the endomorphism inside the endomorphism algebra. Okay? In particular, you see that I've defined now what a special endomorphism is, and to a special endomorphism, I've associated two invariants. one invariant is, well, if you have a special endomorphism that lies in V Betti dual, each class in L dual modulo L will be a well-defined invariant. And then you have a second invariant, which is an integer, which is actually be a positive integer, which is defined intrinsically in terms of the endomorphism algebra of my abelian variety. Okay, so I made the story very complicated, starting from the opposite way of what I should have done. But in fact, this is very natural. Because you see, if you start with V, your vector space, and if you start with lambda in V, an element such that Q of lambda is positive, then I can immediately cook up V lambda, which is lambda orthogonal, and a quadratic form associated to it, a new pair, which is of signature. Well, I removed one of the positive eigenvalues by taking the orthogonal. So I simply have now signature n minus 1, 2. Okay? Aha! But then I can play the game that I did with V lambda. So I can associate to this a group G lambda, which is G spin of V lambda Q lambda. I have my symmetric space D lambda. And actually, my G lambda maps to G, simply because transformations of V lambda I can complete by acting as the identity on what remains, which is the line spanned by lambda. Okay? And similarly, I can identify the symmetric space D lambda simply as the lines in D of C that lies in the orthogonal of lambda. So it lies in DC. Okay? So you see that simply by choosing such a vector lambda, I have a new Shimura variety because I have a group, I have a symmetric space. And now if I take, say K lambda to be my KL intersected, or my K intersected with the G lambda AF, I get a map of Shimura varieties G lambda Q modulo D lambda times G lambda AF modulo K lambda, mapping to my MKC, which is defined in a similar way. So you see that my Shimura variety, MKC, has lots and lots of Shimura subvarieties, which makes its structure very rich, much richer, for example, than the Ziegler modular varieties that has a very nice modular interpretation. So in that sense, it's very good. But it's difficult to find in the Ziegler modular varieties interesting cycles, defining them, studying them, and so on. Instead, here you see you have a large supply of Shimura varieties. And actually, this will define, so this is of dimension n minus 1. This is of dimension n. And in this case, we get a divisor. But you can start playing the same game by taking two such lambdas, which are positive definite and linearly independent. Making the orthogonal, you get as an image a cycle of codimension 2, and so on and so on. So it has a very rich structure. And okay, so you want to tie this up with what I just explained. So if I write this as, for example, when k is equal and n2, just for simplicity, okay, then the image, so let me tie what I did so far. So the image of this map consists of those classes of Z in MKC such that, so we said we have our map from V Betty Z, say even over Q in this case, mapping to the endomorphism of H1A Z Q. So I take my map tensor simply with Q, okay? So these I can simply identify with the Q vector space Z, simply because I have one component, and on the pullback of my local system to D, I simply really have V. So I can talk about my lambda in here, okay? Such that the image of lambda arises as the Betty realization of some F, which is unique in the endomorphism algebra of my Kuga-Satake abelian variety. Okay? So I can describe complex analytically the points where my Kuga-Satake acquires special endomorphisms in the sense that I've defined before, simply by taking the images of all possible lambdas via the map that I've described here. So you see that the loci where Kuga-Satake acquires special endomorphisms, okay? And if you want that your endomorphism lies in the image of V Betty dual with integral coefficients, you take lambda in L dual, okay? So those loci are the images of one-dimensionless Shimura subvarieties. So in particular, they are divisors. So let me write the conclusion here. The locus of MLC where A acquires special endo in the sense above, in the sense given before, is the image of, so let me write precisely what I get, is the image of the disjoint union of all lambda in L dual of d lambda. Okay, so here via the map d lambda to g. So which in our case is really simply the composite morphism. Okay, so you take all those maps. For lambda, I just make lambda in L dual instead of V. so that I get a match with the definition of special endomorphism that I've given before. And I take all those images, and this pans out exactly what I wanted. So my Heegner divisors now, I can give a definition, at least over the complex numbers. So I fix a class mu in L dual modulo L, and an M, which is in fact a positive rational number, and I define Z M mu C simply as, so let me simply write, I will be more precise maybe tomorrow. So for the moment, let me simply write in a bad way the image of all the lambdas that are, so I fix a class mu, so I demand that lambda lies in mu plus L. And I also want that the norm of lambda is equal to M of my d lambda. And let me finish by saying that this classifies so this is the locus of MLC where A to Kugasatake has a special endomorphism F such that F composed F is multiplication by my rational positive integer M. Okay. Two, F arises from a V in V Betty dual of class mu in V Betty dual modulo V Betty that we identified with L dual modulo L. Okay? So this will be the Heegner divisor associated with this pair, M and mu. Of course, there is some compatibility with M and mu to assure that this is non-empty. But except for that, the definition. What remains to be done? Well, first of all, I want to descend this definition to Q. And this is the reason why, instead of considering, and then I'll stop here, instead of considering the image of one single such object for one d lambda, which would give you something irreducible, I group things together in this way. The reason being that while this definition is purely transcendental and analytic, this definition instead, which has to do with the Kugasatake and the endomorphism algebra of Kugasatake and some other object, is, can be in fact generalized and defined over Q that we will do tomorrow. And then I will also briefly mention simply how actually one can sort of extend this definition to integral models. So you'd get not simply Heegner divisors over C, but Heegner divisors over Z. In doing that, I have to be a little bit careful. So I will really have the definition of the Heegner divisors more like these objects, not the image inside my moduli, but well, maybe I'll discuss that tomorrow. Tomorrow, I have to define integral models for my ML. Okay, so here I'll just cite a big theorem and discuss it a bit, and say how actually you can circumvent the limitation that this theorem of Keesing and Basio gives to construct integral models. I will define for you integral versions of these objects that I hope you can sort of start seeing how they are given using our Kuga-Satake. And that will be the first half of the lecture tomorrow. And the second half will be finally the definition of the big CM points and how they relate to our Shimura varieties and why they compute the Faltings-Height for the complete reflex algebra. I'll stop here. Thanks.